Hello everybody, and welcome to the beginning of Chapter 11. This is page 86 of the workbook that we're looking at. And Chapter 11 is about something called the fundamental theorem of finite abelian groups. And this is a very important theorem that gives us a way of describing, in a very organized way, every finite abelian group that we might come across. Okay, so what this theorem is going to do for us is give us a way of, number one, taking any finite abelian group and decomposing it into a very nice form. And then after we've got that decomposition, it also provides an easy way of telling when two finite abelian groups are isomorphic to each other. Okay, so let's take a minute and just read this theorem together. Okay, so two sentences. The first sentence says, every finite abelian group is a direct product of cyclic groups of prime power order. So it's just telling us that we can essentially decompose every finite abelian group into a direct product of this form. Okay, and then the second sentence says, moreover, the number of terms in the direct product and the orders of the cyclic group are uniquely determined by the group. We're going to see that that second sentence gives us a way of looking at two finite abelian groups and telling whether or not they're isomorphic to each other. We'll kind of see how that works when we do some examples together. Okay, now there's one kind of important, nice observation that we can make on the tail end of this. So you might remember from earlier in the course, every cyclic group of order n is isomorphic to Zn. Okay, so that fact allows us to be a little bit more specific. Okay, go back to Theorem 1.11, make a little bit more of a specific statement. Okay, because it's possible to describe every cyclic group in this sort of a form, it tells us that every finite abelian group can be broken down as follows. Okay, I'm just going to write this decomposition down and then we'll maybe talk about the high points of it together. Okay, and I want to make one note, the P1, P2, P3 up to Pk, those are primes. I'm assuming that those are primes. Okay, so it just says that we can decompose any finite abelian group like this, okay, into a direct product of Z of a prime to a power, basically, okay, because of the fact that every cyclic group is really isomorphic to something that looks like Zn. All right, so all of that said, let's do some examples, okay? To conclude this video, we're going to look at just part A of example 1. Let's take a minute just to read the directions of the example first. So it asks us to determine the number of non-isomorphic abelian groups of each of the following orders, and then to write down a group from each isomorphism class. Okay, so part A would like us to do that for order 9. Okay, it's asking us how many non-isomorphic abelian groups of order 9 are there? Okay, well, what it comes down to really is kind of the number of different ways that we can break up the prime factorization of 9. Okay, so the first thing we might notice is that 9, okay, can be written as 3 squared. Okay, or if we wanted to, we could break that down into 3 to the first times 3 to the first. We could take that 2 and split it into 2 pieces. And so what the theorem is telling us then is that there are exactly two abelian groups of order 9. Okay, one of them is going to look like Z9, okay, kind of putting the 3 squared together, and the other one's going to look like Z3 plus Z3. Okay, it just takes the 2 3's and splits them apart. Okay, this turns out to be our answer. And so, if we believe this answer, that means that there are exactly 2 of them. 2 non-isomorphic abelian groups of order 9. Okay, now, how do we know that those 2 groups are really not isomorphic to each other? Okay, let's think about that for a minute. One way to see that from the theorem is by looking at the second sentence in the theorem. Okay, and specifically the part of that sentence I'm looking at is the number of terms in the product. Okay, notice that Z9 has just one term. Okay, there's no direct product there. We've just got Z9. And Z3 plus Z3, that has two terms. Okay, the fact that those two numbers are not the same, the number of pieces are not the same, tells us that these are non-isomorphic according to this theorem. Okay, you might be able to think back to earlier on in the course and maybe be able to come up with some other reasons why these two groups are not isomorphic. For example, Z9 is cyclic and Z3 plus Z3 is not. Okay, that concludes our first video of this chapter, and in the next video we'll continue with this and do a few more examples using this theorem to come up with trying to list out the number of possible groups.